Okay, we're recording.
Okay, well, we're very happy to have Jonas Haferkamp with us today from Jens Eisert Group at Free University in Berlin to tell us about some really interesting recent work concerning the growth of quantum complexity and randomness. Jonas, take it away.
Thanks a lot for the introduction and thanks a lot for having me. As you announced, I'm going to talk about quantum circuit complexity and random quantum circuits and how the tool or the concept of randomness helps to establish quantum circuit lower bounds here. I want to talk about two results of mine. The first one is upcoming work, and the second one is joint work with this wonderful group of people. So there's Felipe Feist, Naga Kutakonda, Jens Eisert, and Nicole Junger-Halpern. And so during this talk, I would like to share with you some of my intuitions that I have about these results and how seemingly very different approaches have the same underlying ideas, and also some very surprising technical similarities. So having said this, let's dive right in by introducing the key concept that this talk is going to be about. I want to talk about quantum complexity, and quantum complexity is really a ubiquitous concept in quantum information theory, quantum computing, and overall computer science. It's not very surprising because on an extremely high level, quantum circuit complexity just measures or quantifies the amount of resources that you need to implement operations. And obviously everyone, whether practically interested or theoretically minded, wants to know how many resources they actually need to implement their operation or their state. So long before there were serious efforts to build a quantum computer, the classical analog of quantum circuit complexity was already around and one of the most pervasive objects in theoretical computer science. Here it is related to the separation of complexity classes, like the question P versus NP. It is related to communication complexity and to derandomization of complexity classes. So it's really everywhere, and some of the best approaches to long-standing open problems are based on lower bounding quantum circuit complexity. But I'm going to talk about this a bit more later on. The quantum notion of quantum circuit complexity, even though, as I'm going to explain, it has sort of a computer science flavor, makes some very surprise appearances in actual physical systems. So for example, the notion of a topological phase of matter can be defined using quantum circuit complexity. Usually when you talk about topological phases, you talk about a family of ground states, of Hamiltonians, that are described by some uniform family of local summons, and you want to know whether this is in a topological phase or not. And one can define this to be the case if there is no constant depth circuit preparing the state or the family of states. So in order to say that a given family of ground states of Hamiltonians is actually in a topological phase, to prove this, you would have to establish circuit lower bounds that are super constant. Then a different application that is a little bit more sci-fi from my perspective, and a little bit very close to the home turf of at least, I think, 50% of the audience, is the ADS-CFT correspondence, where also quantum circuit complexity seems to make a very surprise appearance. But this is also something that I'm going to talk more about later. So before I go to talk more about the ADS-CFT correspondence, let me specify what I mean exactly when I say circuit complexity. Oh, doesn't it work? Wait a second. Ah, here it is. Good. So, sorry. It is kind of a folklore result in quantum computing that every unitary can be exactly implemented using finitely many two local gates. In particular, you need at least, at most, 4 to the n times something that scales like a polynomial many. You can find this result, for example, in classical textbook like Nielsen and Schwann. On the other hand, we can always ask for any given unitary, what is the minimal decomposition, or what is the minimal number of gates that we need to implement our unitary? And this is what we call the circuit complexity of the unitary. And very similarly, for states, we can define it exactly the same way. And maybe now is a good point for me to point out that basically everything, sometimes I'm going to talk about unitaries and sometimes I'm going to talk about states and the complexity of states or of unitaries, depending on what makes more sense in the context. But every time I make a statement about the complexity of unitaries, there's an analogous statement for the complexity of state that can be obtained by very similar methods. So it really doesn't matter. It's like, I'm just restricting to special cases for time reasons mostly. So of course there are various different notions of quantum circuit complexity, all depending on what we mean by implementation. So for example, a very traditional or old notion is that of exact circuit complexity. You could also call it, for example, the synthesis complexity of a unitary, where you actually require the unitary to be exactly implemented, and then you minimize over the number of gates that realize this. Another one is where you allow a small implementation error, and you only want to find the minimal number of gates that you require to approximate your unitary. For example, in the diamond norm, which is a very operational measure of distance between unitaries. Actually between channels, but you can consider the twirl. Sorry, if that was too much detail. So here you could pick, for example, some small epsilon and then consider the approximate circuit complexity. So with this notion, something that I want to mention, because I'm going to because some of you are going to ask this anyway. There's also a notion of complexity defined by Nielsen that that is based on a new Riemannian metric on the unitary group that penalizes high locality time evolution. And this notion is somewhere between these notions in a sense. So it turns out that the exact circuit complexity always upper bounds this Nielsen geometry, and there's always a polynomial in the approximate circuit complexity that lower bounds the Nielsen complexity. So for every small error, we can somehow find a lower bound that depends on this error. Okay, so finally, so now that I have specified what I'm going to talk about, the ADS-CFT correspondence. It is this proposed dictionary between a gravity theory in the bulk, in a d-dimensional gravity theory and an ADS anti-de Sitter background, and a quantum theory on the bulk, on the boundary. And the problem that was identified here by Susskind and co-authors is that apparently in the ADS theory, certain wormholes seem to have a volume that grows steadily for an exponentially long time. But this is somehow very surprising, because if this corresponds to a local observable in the CFT, well, we kind of know or expect local observables to thermalize or equilibrate extremely quickly, so this quantity should saturate after a very short time, if our intuition about quantum theories and local observables is correct. And the proposed solution for this by Susskind and co-authors was that maybe the volume of the wormhole actually doesn't correspond to a local observable, but it somehow depends on an intricate, complicated global property of the state. And one possible solution for this dictionary would be complexity, because we expect it to behave exactly like the wormhole volume. Lately, I've seen other proposals. There's also the complexity equals action proposal that was put forward later. And lately, I've seen a paper that says complexity equals anything, almost anything, where people came up with an infinite family of quantities that could, in principle, also correspond to complexity. But for me personally, the intuition that was obtained from this for the complexity is the most interesting part. So what is the idea, the intuition that was obtained? Adam Brown and Leonard Susskind, they put forward a conjecture about how complexity should grow in order to behave as the wormhole volume does in the ADS bulk theory. And the idea behind this is that for a very long time, there's basically no reason to get back close to a low complexity unitary. So here it is in words. The conjecture is that for a typical interacting system, Like, let's think about some generic system that you would maybe find in nature also. The circuit complexity should grow for an exponentially long time linearly and then saturate. Well, why do we believe this? Well, first of all, we kind of know that this is true at very early times. So for polynomially deep time evolutions, it is kind of well known that entanglement is generated at a sort of linear rate. And from this, you can actually easily obtain quantum circuit lower bounds, because you need a certain circuit of a certain depth to generate enough entanglement. Yeah, I see there's a question by Elliot Rosenberg. You can, I would be happy to answer it now. I think you're muted, like at least I don't hear you.
You can't hear me?
Yeah, I can hear you.
Oh, okay. So I'm just wondering, I mean, this is a basis dependent statement, like the complexity of a particular state. So like if the starting state for your quantum circuit is the target state, then you don't need to apply any gates in order to get to the target state. So is it, when you talk about the complexity of an actual state, is that like starting from a random state, or what do we mean?
It is not necessarily basis dependent. It is dependent on the tensor structure of your space. So if you write your space as like a tensor power of local spaces, then there's different ways of factorizing your state into these, right? Mm-hmm. And then the natural thing, or to say how complicated is your unitary, is to define it as the number of unitaries, local unitaries that you need to arrive from a product state, because every one local unitary you can anyway absorb into two local gates.
Right.
And then if you use a different tensor product structure for your Hamiltonian, then you're right, then something completely different could happen. But I would argue that nature maybe provides us with a natural tensor product structure. And if it doesn't, then we run into all kinds of different problems. Like then all of many-body physics becomes very weird. Like, because then even the concept of local interaction doesn't make sense anymore.
Right, right.
Does that make sense?
Yeah, yeah, it does. I guess you run into problems with like fermions and things like that, because fermions don't really. Yes,
fair enough. I mean, to some degree, you can map fermions to qubit systems, but these mappings are not local, right? Like Jordan-Wigner mappings, yeah.
Yeah.
But I haven't, for this at least, I haven't considered fermionic or bosonic systems.
Right. Okay. Thank you.
Cool, thanks. So, as I said, for early times, we are generating entanglement. But the problem is entanglement entropies also saturate comparably quickly. So for example, for random circuits, after like linear depth, we would expect that along bipartite cuts, the entanglement entropy is essentially maximal along every cut. And it also means that our circuit lower bounds that we get from this do not keep on growing. So one way of thinking about this that I really like is of circuit complexity as sort of a fine-tuned measure for entanglement beyond the saturation of entanglement entropies. Because what circuit complexity really measures for a state, for example, is how many unitaries do you need to rotate your state back into a product structure, into a separable state. And in this sense, it really does measure the difference, or in some way, the difference between a product state and your state. And the idea is that the true measure of entanglement that keeps on growing until we finally saturate when we meet basically all states is circuit complexity. The other reason why we believe this is that the unitary group and also the state space are vast spaces, gigantic spaces of exponentially large dimensions. And in particular, as I'm going to explain on one of the next slides, the set of basically in these gigantic sets, the low complexity unitaries or states are extremely rare. And for this complexity growth to stop early, we would kind of need to hit accidentally one of these lower complexity unitaries or states. And the idea is that as these are so rare, this shouldn't happen typically for systems. Well, if this is so obvious, and it kind of should be from what I just said, like that this is very likely to be true, then why is it a conjecture and not a theory? The problem is, as you see in this picture, it is very hard to disentangle any specific unitary. So if I just give you some efficient description of a unitary, I bet a lot of money that you won't be able to give me the exact circuit complexity. I already mentioned that the classical analog is related to notorious questions like the separation of complexity classes. And very similarly for unitaries, I personally don't know of a single example where there is a super polynomial lower bound, and I can give you like a single example of a family of unitaries that can be described efficiently somehow where there's a super polynomial complexity lower bound. And that even though most unitaries are extremely complex. And the problem is that while I said earlier that the low complexity unitaries and states should be extremely rare, they don't seem to have a lot of structure that we can exploit. So while they are rare, if you have just a given unitary, there's basically no way of ruling out that there's like an accidental shortcut nearby. And if we could rule it out, like, what would that mean? Basically, we would have to characterize the set of all unitaries that can be approximated with a low complexity. And to some degree, if we had such a characterization, maybe then the computational power of quantum circuits wouldn't be such a mystery. I mean, of course, this is not a rigorous argument, but this is sort of how I try to make sense of the difficulties here. Well, how to make progress if it's so difficult? One way of going forward is basically to assume that certain complexity classes don't collapse. And that leads to really cool results. So for example, there are Hamiltonians, specific Hamiltonians for which you can show that after a super polynomially long time, actually the complexity, circuit complexity of the states that you generate has to be super polynomial as well. So there's results, for example, by Aronson and Susskind and Brandao-Bogdanovic, which show exactly this. The only problem here is that they require computational complexity assumptions. Usually these are benign and very well believed. So this is more than just like evidence that this should be true. But here in this talk, I want to focus on unconditional bounds. And if we really want to prove unconditional bounds that do not depend on the non-collapse of certain complexity classes, then there's a clear way forward, and that is to consider a certain toy model. If you tautorize a Hamiltonian, you can always discretize a Hamiltonian, then you are going to end up with a sort of natural structure of a circuit describing this Hamiltonian, where you sort of have brickwork layers, and time is basically the number of layers. And in this toy model, we introduce a certain time dependence, where we draw each gate at random uniformly from the 2-qubit Clifford group, or from some fixed gate set, depending on the model. And I write here Haar measure, but it's just a fancy word for drawing it uniformly. And we draw all of them independently. And I just want to mention, this is the idea to make progress here. I have this from a paper by Brandao, Chemisani, Hunter, Jones, King, and Preskill that was very influential to me when I first came up with these questions. So the cool thing is, for most unitaries, why are random circuits any better than like a specific Hamiltonian? Well, I already kind of hinted at it by saying that the only things that we can say is that certain sets are rare and certain sets are not so rare, but we don't have a lot of structure. And the point is that random circuits very quickly seem to generate sets that have probability distributions on the unitary group that have properties that are very similar to the global uniform distribution, like the completely uniform distribution on the entire unitary group. And for this full-blown uniform distribution, there are actually very simple counting arguments that show that most unitaries have to be very complex. So how does this work? It turns out that locally, if you just consider a small point, this distribution basically looks like the volume of a Euclidean space. And therefore, if you consider a small ball and, for example, a Riemannian metric, basically what you see is that the volume is going to be exponentially small in the dimension, and since the dimension is exponentially large, these balls have volume that is doubly exponentially small at the system size. Well, and then you can consider the set of MR of all quantum circuits that have R gates and that you draw from a gate set, and you observe that these are at most G to the R many unitaries. But unless R itself is also exponentially large, these are not going to be doubly exponentially many unitaries. So you simply don't have enough patches of small local balls around these unitaries to generate the full unitary group or even a small fraction, unless you have exponentially deep circuits. So the idea behind both results is essentially to de-randomize such counting arguments for the full uniform group. And a key notion here, for the first result at least, is that of unitary designs. Unitary designs, for everyone who doesn't come from the quantum info community, and probably also for many who are not in the quantum info community, are essentially pseudo-random distributions. That means if you sit at home and you compute expectation values over a unitary T design, which is a probability distribution on the unitary group, and you have like a friend and you call this friend, and this friend actually computes expectation values over the full Haar measure, and you call them up and you both computed the same function, then you will say, well, okay, wow, we both have the same results all the time, as long as I only compute expectation values over a degree T polynomial. So you will never be able to distinguish this using only a degree T polynomial from uniform randomness. And there's sort of a very cute toy example that I personally like a lot, which is the circle with the smallest unitary group, essentially, where to only have the same expectation value as integrating over the circle, it suffices to have 2 points that are diametrically opposed, like 1 and -1. You add them up and you get 0, which is exactly the same that you get if you just integrate over e to the I phi. But if you square this, if you square e to the I phi and you integrate over it, you still get 0. The problem is for the set, you don't get 0 anymore because you cancel the phase. And it turns out if you have equidistant points, 3 equidistant points, you get the same property even for squares, and so on and so on and so on. And if you have like higher and higher, better and better equidistributed polygons in the circle, you will never be able to distinguish the expectation value over these points, sets of points, or over the full unitary group, which is the circle. And a very similar thing works for the unitary group, even though these sets of points will be much more complicated, unfortunately, than just polygons. Well, the cool thing about this is, for these sets of distributions, we can actually establish circuit lower bounds directly. Oh, is there another question?
This is a very basic question.
Yes.
When you say polynomials,
yes,
polynomials of what? Polynomials of what?
Yeah, thanks for letting me clarify this. I actually forgot this. Right. So it's polynomials in the entries of the unitaries. So actually, I lied a little when I showed you this example, because here the polynomial is the entry of the only entry of the unitary, which is e to the I phi. But for unitaries, we actually consider polynomials in U and U bar, meaning U complex conjugated, to rule out that you just have an extra phase and always get 0. So this definition that we actually use for the definition of a unitary T design that you will see if you look it up in a paper or somewhere actually rules out these examples because it always kills all of the phases. But essentially it's polynomials in the entries of the matrix that gives you the unitary. Does that clarify it?
So if polynomials in the particular random unitary that you're also evolving this with?
Yeah, so for example, you have a unitary and a random unitary, and you always consider the first entry, the absolute of the first entry to the T. This would be a polynomial, and you can compute the expectation value over this first entry. And
I see.
If you have a unitary T design, you will always get the same thing as a unit, as if you compute the expectation value over the full unitary group. Okay, so if an ensemble has this t-design property, this pseudo-randomness property, it turns out that you can get from this a lower bound that is linear in t, even for an approximate notion of circuit complexity. And I want to be very ambitious and show you the derivation, because for me it was extremely illuminating when I first saw it, and I was kind of surprised at how simple it is. So I have essentially, the argument comes from this Brandao, Chemisani, Hunter, Jones, Küng, and Preskel paper. And I should say they also do a lot of other things and very complicated things in that paper. But this particular derivation is actually surprisingly simple. So let's here consider, for example, two states, psi and phi. Phi is drawn from a t-design, and psi is any state that you can reach using at most R gates. So you have at your disposal all circuits essentially with at most R gates, and you can use this, and you start with a computational basis state, and you can try to reach this, this state psi. And the point is among all of these states psi, any state such that psi and phi have an overlap that is larger than 1 minus, let's say, some very small constant delta. Well, what you see here in this probability bracket is basically something that I would call an OR. Like, it suffices for any psi to be the case. Like, you don't need this to be the case for all psi, just like one psi, if you have that, then basically this is satisfied, since we have a max here. And it means we can definitely upper bound this simply by all of the probabilities that that this is the case for some psi in MR, in the set of states that you can reach with at most R gates. And for this one, we can now do something that's really cool, I think at least. Well, the probability that this overlap is larger than 1 minus delta is obviously just the same as the probability of this overlap to the 2t being larger than 1 minus delta to the 2t. I can just take the entries to the 2t and the equality stays true or false, depending on what's the case. Well, but for this probability, I can now simply apply the Markov inequality directly and obtain an upper bound of the expectation value of the overlap to the 2t divided by this 1 minus delta to the 2t. And the cool thing that makes this work is that if you substitute this expectation value from your t-design by the expectation value of the unitary group, which you can, because this is a polynomial of degree t, actually of 2t, but it's a degree t polynomial in the entries of psi and the complex conjugate of psi. So you count these individually, actually. If you do this, you see that this expectation value is actually incredibly small. And this expectation value here, because it's the Haar measure, doesn't depend on the state or depend at all on the structure of this psi. So we simply get the sum of all of these states that can be reached by this. Like, this will be extremely many times this bound. And the cool thing is that this bound is small enough to still rule it out, because now it looks like this. This expectation value, it's sort of a standard calculation if you compute moments over the Haar measure a lot, is actually small as 2 to the n plus t minus 1 over t to the minus 1. Actually, this is the dimension of the t times symmetrized space of n qubits. And then you still have this 1 minus delta to the minus 2t, and now you have this suddenly very large factor that depends somehow on your gate set, on the size of your gate set, but this is a constant to the number of gates. But because this thing here, this 2 to the n plus 1 minus plus t minus 1 over t is so gigantically large, basically just choosing t to be linear in R suffices to kill this factor completely and make this exponentially small. So as long as we are allowed to choose t linearly large in R, and as long as t is not too close to 2 to the n, let's say, at some point this bound saturates a little. As long as this is the case, we can make this probability of having overlap with any of these states exponentially small. And so in a sense, we just say a unitary t-design just has too many different states that are too far away from each other necessarily to have any overlap with a high probability with any of the low complexity states, simply because there are too few of them. Okay, so let's just say what we can say about circuit complexity from this. There's a seminal result by Brandao, Harrow, and Horodetsky who show that random quantum circuits, and so this is how I'm getting back to random quantum circuits now, actually generate these pseudo-random distributions in a depth that scales like t times t equals the system size times t to the 11. And since this paper came around, there were some improvements in certain regimes, but essentially for qubit circuits, I would say it's still the best result around. And basically you just have t to the 11 since 10 years, essentially. And if we just plug this into a linear lower bound for T designs on the circuit complexity, we now get a lower bound that scales not linearly, but at least like an 11th square root for an exponentially long time. So this is already very close to the, this is already very close to the Brown-Susskind conjecture in a sense that it works for a very nice notion of circuit complexity, basically for any robust notion that you can come up with. And also it works for an exponentially long time, and it has sort of a flavor of linearity already. So the first result that I want to talk about is an improvement of this bound. Oh, wait, here we go. So this is the first result of this upcoming work. I think for the first time in 10 years, I can improve this exponent, and I can show that random quantum circuits form unitary T designs in a depth that doesn't scale like T to the 11, but actually like T to the 5 plus something that is very small. And obviously, just plugging this into the same bound now also gives us a much improved lower bound on the circuit complexity. So what I want to talk about next is how can this be improved, this bound? I don't want to get too much into the details because it's a very long and complicated paper. But I kind of want to explain some of the techniques that go into it in order to emphasize the parallels to the second result that I'm going to talk about. And for this, I need you to follow me a bit to the Cliffords. The Clifford group is a magnificent algebraic structure that lives in the multi-qubit unitary group. So it can be defined in various different ways. The most boring one is just, you can say, it's a set of unitaries that you generate using phase gates, Hadamard, and controlled knot. A better definition would maybe be the set of all unitaries such that if you twirl a Pauli operator, you end up with another Pauli operator. And also there are more fancy definitions that basically identify the Clifford group up to a factor with the symplectic group on F2 on a vector space over finite fields. And it turns out that, well, actually, I should say the Clifford group as we know it and the unitary group is then a representation essentially of this symplectic group. It can also be seen, which is more hand wavy, it can be seen sort of as an analog of Gaussian operations in the discrete setting. This, as I said, this algebraic structure has magnificent properties. So first of all, if you don't count phases, at least, it is a finite group, which is amazing. Each of these unitaries, by a result by Gottesman and Aronson, actually, I think this was known before, but like they improved the complexity, is polynomially bounded. And even though they are all polynomially bounded, the entire group, if you draw uniformly from it, still has the two design property. And this can be used to actually improve this bound by Brandao, Harrow, Horodetsky, at least by cutting it in half almost. Like the lion's share comes from this. And the idea is that at least one half of the proof of this Brandao, Harrow, Horodetsky result comes from a convergence of this local random walk, that is random quantum circuits, against the Haar measure eventually. So you can see in some sense of closeness of distribution, this will be very close to the Haar measure. And they use something that's called the path coupling technique on unitary groups. So maybe some of you are, especially the more computer sciencey, like people that like, how do you say this, Monte Carlo simulation and Monte Carlo algorithms, they usually know the path coupling technique. And there's an analog of this for the unitary group. And it turns out that this converges in exponential time, and the exponential that they find is like 1 over e times 5 to the n, which is far from optimal because the dimension of the unitary group is actually 4 to the n. And we would expect actually that convergence to the optimum happens shortly after we reach the dimension of the unitary group and numbers of gates. And it turns out that there's a different walk, which we considered in a somewhat unrelated paper, actually. But this is where I know it from, this walk. This is where you alternatingly consider a global Clifford unitary and then a single qubit random unitary. And you alternate this or interleave this for some time. And it turns out that this walk, with the same technique, basically, converges almost optimally up to polynomial factors, which don't matter if you have a computer science mindset. And then what we can do is we can use the properties that I named above, namely that it's a finite group and that it's polynomially upper bounded. We can use this to approximate the uniform measure on the Clifford group in polynomial time, essentially, with a local random walk. And then we can use this to relate this to a local random walk. Let's just keep this in mind when I talk about the second one, because the second result comes now. And the question is, we have like a sublinear growth already for a very robust notion of circuit complexity, but can we actually prove linear? And I say for this traditional synthesis definition of circuit complexity, this is actually the case. And it is the case because of a different counting argument. The point is that the exact circuit complexity is susceptible also to dimension counting and not only to volume counting. In particular, the dimension of the unitary group is 4 to the n, and we can simply consider the set of all unitaries that are generated with at most r gates. And here we even allow any two local gates. But simply because the number of gates times the number of parameters per unitary group upper bounds the number of parameters in the set, we will always have a lower dimensional set. Is that clear? Because we simply have at most 15 parameters per gate, and we can only add them up. So unless we have exponentially deep circuits, we are going to end up with a lower dimensional subset. And this lower dimensional subset is always going to be of measure 0, necessarily, because we don't have enough parameters. And the idea for the second result is to de-randomize precisely this counting argument. Namely, we now have to lower bound the dimension of the set of unitaries that can be generated in this brickwork architecture. If we have a lower bound that scales linear with the depth, then we also know, because the other upper bound is also linear, that less than linear circuits will always make up a measure 0 subset, necessarily, simply by dimension counting. And I should say, it's a bit difficult somehow to make some of these things rigorous, but what we achieve basically from this is that we have taken this extremely complicated mythological creature that is the circuit complexity of the time evolution of some Hamiltonian, and we have replaced it by something that is comparably tame. And it is tame because we can use a toolkit from topology and semi-algebraic geometry to lower bound this dimension. In particular, what we do is, using semi-algebraic geometry, we reduce this to a combinatorial problem. So imagine you have a circuit and you can choose any circuit with, like, actually, I should say in brickwork architecture, this circuit is a little bit more general, but let's just stick with any circuit. If you have a given circuit architecture, and now I allow you to insert Pauli operators after gates, like one at a time. Basically, you can insert a Pauli operator here, or you could insert a Pauli operator here, or here, or here, and so on, and so on, and so on. And in this fashion, the question is, how many linearly independent unitaries can you obtain? Well, of course, if I have like a gate here and a gate here that is the identity, and I insert here two Pauli operators, two local Pauli operators, and here another one, then I don't get much new linearly independent matrices. And that makes, of course, sense, because if you add a gate after another gate, then it can always be swallowed into the previous gate, so you don't increase the numbers of parameters. And the idea is now to lower bound this number of different linearly independent matrices, and thereby lower bound the dimension, and thereby de-randomize the counting argument that tells us that most unitaries should have very high exact circuit complexity. So how do we do this? We pick Clifford gates, because Clifford gates have the 2 design property. And for the Clifford group, it turns out that the 2 design property is equivalent to the fact that the Clifford group maps all non-trivial Pauli operators to all non-trivial Pauli operators. And for us, it suffices that we can reach every Clifford operator. So the point is, we can now, for example, move all of them to the right, commute them through this Clifford circuit. And what you get here, for example, we inserted a Pauli operator here, and this is, if these are our Clifford, this is the same as having a non-trivial Pauli operator here that depends on this Pauli operator and on these 2 gates. And the idea is now to have an inductive construction. So assume that we have already T circuits. Actually, I should have, okay, T circuits of a given architecture. So this is from, this is a bit more general than brickwork, but the same argument holds for brickwork. And that we generated via this process here already T prime many Pauli operators, different Pauli operators. And these are orthogonal in the Hilbert-Schmidt product, so they are all linearly independent necessarily. What we can do now is, in the same architecture, we can pick a circuit that rotates any Pauli operator that is not in this set to a single qubit Z operator. We can show that this is always the case for a brickwork circuit of a certain depth, and also for these circuits that are a bit more complicated. And because this Pauli Z operator comes after a gate, it is now in the span of the set of matrices that we can obtain this way. But since we assume that these are all the Pauli operators that we generate from this part of the circuit, and we have chosen this Pauli string to be not in the span, which we can always do unless we have already generated the entire unitary group or all of the Pauli matrices. This new Pauli string is one of the matrices that we can obtain this way, and it is linearly independent. And therefore, for each chunk that is like deep enough, let's say of linear depth, we can generate one new linear independent matrix. And in particular, we can also lower bound the dimension from this directly. So what do we obtain? What's the result that we obtain? Finally, here it is. It's the Brown-Susskind conjecture for exact circuit complexity. We show that if you draw U from a random quantum circuit in a brickwork architecture, then we can upper bound the complexity by the number of gates divided by 9 times n squared minus n over 3. And actually, this n over 3, we can get rid of it by just changing the scaling here slightly. The idea is that if you have a computer science mindset, these are only polynomials which scale logarithmic in the number that we really care about, which is the number of gates. Because the difficulty is in establishing such a lower bound for exponentially deep circuits. And for exponentially many gates, these are very small and essentially effectively constant. This holds not only with probability 1, it actually holds until the number of gates is not just an exponential, but essentially, again, up to polynomial factors maximal. So it really scales like the dimension of the group. And so we finally have the linear growth of circuit complexity. And for some notion of quantum circuit complexity, this is actually the Brown-Susskind conjecture. So the way I think about it is we pick a toy model and we pick a very restrictive notion of quantum circuit complexity. But we obtain the full linear growth and the saturation. So for me, this is essentially a minimal version of what Brown and Susskind conjectured. Like sort of the minimal version that you could possibly prove. But it is a proof and it does work out. Well, what do I want to do with this? I think essentially, at least for not so deep, not exponentially deep circuits, the proof that the bound that I presented here can be much improved. Essentially, we can generate many more linearly independent matrices if we don't have this exponentially deep restriction. So I think, for example, essentially for polynomial depth circuits, most local random circuits are actually perfectly incompressible in the sense that each local random circuit is its own minimal circuit description. Like there's no way of compressing it even a little. And this should hold with probability 1. Of course, if you pick all of the gates with the identity or something like this, some very accidental low probability constellation, then this doesn't hold. But with probability 1, I'm pretty sure it holds. And so far, I can show this, or I should say, with some collaborators, I can show that this holds until the depth of the circuit is like scales like n squared. But I'm pretty sure it can be pushed farther than that, and I would be very interested in pursuing it. Another thing that I'm very interested in is monitored circuits, or notions of complexity for mixed states. So here, for example, there are some very interesting results where people observe phase transitions in, for example, the entanglement entropy if the certain rate of measurements is performed in local quantum circuits. And I would like to see if circuit complexity undergoes similar phase transitions. And then for me, obviously, the big one is proving the Brown-Susskind conjecture for a very error-robust notion of circuit complexity. And maybe I end on a sort of personal assessment of that. It looks like we are closing in on the problem from various different approaches and sides. But for me personally, it feels like the closer we get to it, the more it feels like squeezing maybe water out of stones, or like the problem actually fights back. So either it's not true, depending on the notion of error robustness, or there's some very profound statement hidden here, or we simply don't understand everything about it. So I don't know exactly how it looks like, a solution to this problem, but I have a pretty good idea that, or I think it's very likely that the Clifford group is going to play a role in any solution. So I think I stop here. Thank you very much for the attention, and I would love to answer any questions.
Great, thank you, Jonas. That was a fantastic talk. Yeah, let's see. Should we have some questions for the audience?
Let
And
me
maybe
stop
I'll be on
recording
you.
and
Yeah, good.
then ask questions.